In this video, I'm going to introduce you to a concept called differentials. I'm going to explain to you exactly what they are. However, differentials are based on linear approximation. And that's what the previous video was all about. So if you didn't get a chance to watch the previous video, you need to jump back and watch that video first so that this video will make more sense. I'll put a pop-up link up in this area somewhere. But the bottom line was, if we are close to the point of tangency, the tangent line and the actual function are so close together that we can often use the tangent line as a good approximation for the function. And specifically, if the point of tangency is at an x value of c, we learned that the equation of the tangent line is always going to be y equals f at c plus f prime at c times x minus c. So we have this x value of c. Now imagine that we want to investigate what happens at another x value that's nearby. So we'll call this x. First of all, these are going to correspond to two y values. The c will correspond to a y value of f at c, and the x will correspond to a y value of f at x. However, the space between these x values, right, the difference between the first x value and the next x value, can be called delta x. So we can name this second x value, instead of just calling it x, we can call it c plus delta x. All right, so we have, so another way to describe these two x values is c and c plus delta x. So using those names of the x values, we can describe the corresponding y values. We still have f at c, but we can think of the next y value as f at c plus delta x. Differentials are all about the change in x and the change in y. So the change in x is going to be x2 minus x1. So using the yellow names, that's going to be c plus delta x minus c, right? x2 minus x1. So that's the change in x, so we can always call that delta x. Using the blue names, the change in x will be x minus c. So that's also delta x. What about the change in y? Using the yellow names, y2 minus y1, we are looking at f at c plus delta x minus f at c. So that's the change in y, so that's delta y. Using the blue names, that's going to be f at x minus f at c. So we would have f at x minus f at c. So that's another way of writing delta y. But here's where the differential comes in. What if instead of f of x, the actual function, I wanted to use the linear approximation? So first of all, the change in y, delta y, will be approximately equal to whatever I'm about to say, because I'm about to substitute for the linear approximation. So remember, the linear approximation is all of this. So I'm going to substitute the expression for the tangent line, the linear approximation, will substitute instead of f of x. So delta y is approximately equal to all of this. Notice that we have f at c and then minus f at c. So those are going to cancel each other out, and we're going to wind up with delta y is approximately equal to f prime at c times x minus c. Remember that x minus c is just delta x. So I can write delta y is approximately equal to f prime at c times delta x. So here's where the differential comes in. We're doing an approximation. In the context of an approximation, instead of using delta y and delta x, we use dy and dx. So this becomes dy equals f prime at c dx. The essential question of this video is, what are differentials? So here it is. dy is the differential of y. That's the change in y of the linear approximation. Dx is the differential of x, and that's the change in x used in the context of an approximation. So here's the formal definition of differentials. But the bottom line is the differential of y, or dy, is equal to f prime of x dx. And yes, that's the formula that we just spent the whole video coming up with. But I want to emphasize to you the difference between delta y and dy. When we are talking about the change in y of the actual function, we will write delta y. And that's going to equal f at x plus delta x minus f of x. Basically, y2 minus y1. When we are talking about the change in y of the linear approximation, we will write dy, and that's equal to f prime of x dx. When you're close to the point of tangency, delta y is approximately equal to the differential. So we will often use the differential to approximate the change in y of the actual function. For example 1, we are comparing delta y and dy. In other words, we are comparing the actual change in y with the linear approximation. So let y equal x squared. Find dy when x equals 1 and dx is 0.01. Compare this value with delta y for x equals 1 and delta x equals 0.01. We are going to need the first derivative. So y prime is going to equal 2x. So let's start with dy. We've just now learned and we are memorizing that dy equals f prime of x dx. So that means dy is going to equal, so f prime, that's your 2x, but we know what x is. X equals 1. And then the dx is the 0.01, so times 0.01. And this is going to equal 0.02. So that's dy. Now let's compare that with delta y. So delta y is always going to equal f at x plus delta x minus f of x. This is y2 minus y1. So delta y is going to equal, so we're talking about f, that's the original function x squared. So we're doing something squared minus something squared. But first, we're squaring x plus delta x. So that's 1 plus 0.01. So that's 1.01. And then second, we're just squaring x. So we're just squaring 1. So in that case, delta y is going to equal 1.0201 minus 1. So that equals 0.0201. So compare what we got from the linear approximation with what we are getting for the actual change in y. Look how close these are. Let's take a look at this table that will allow us to compare the values of the function to the values of the linear approximation for x values that are close to the point of tangency. Speaking of the point of tangency, when they said when x equals 1, and later compare the values with delta y for x equals 1, that x equals 1 is telling us that 1 is going to be where the point of tangency is. So notice that as we move from the point of tangency of 1 over to an x value of 1.01, the change in x is the 0.01. So this is the delta x, or we could call it dx. Now, the middle row is the actual function. So as you look at the middle row, you can see that this part of it is the change in the y values. So the actual change in the y values is called delta y. So that's what this is. And then the third row is the linear approximation. So this 0.02 is the change in y of the approximation. So that's what dy is. And remember, the essential question for this video is, what are differentials? And here they are, the dx and the dy, these are the differentials. Let's briefly look at one more column. This time, the change in x is 0.1. So that's your dx. The actual change in the y value is 0.21. So that's your delta y. And the change in the y value of the linear approximation is 0.2. That's your dy. Notice that for x values that are closer to the point of tangency, the actual value of the function and the linear approximation are closer together. But as you choose x values that are further away from the point of tangency, then the actual value of the function and the linear approximation get further apart. Speaking of linear approximation, before I end this video, let's do a quick review of where this linear approximation equation comes from. Here's the formula for the equation of a tangent line if C is where the point of tangency is, in this case 1. Let's not forget that the derivative of f prime, in this case is going to be 2x because of the power rule. So substituting in what we know, f at c, function f is x squared, so this is going to be x squared at 1. And then next we have f prime at c, so that's 2x, again at 1. And then we have x minus c, which is just going to be x minus 1. So then it's just a matter of simplifying this. So this will be 1 plus 2 times x minus 1. So that's going to be y equals 1 plus 2x minus 2 with the distributive property. But when you combine like terms, you end up with y equals 2x minus 1. So that is where this linear approximation equation came from.